science lecture, a series presentation. Our presenter, Niall Clancy, is a Ph.D. candidate at the University of Wyoming. He holds a bachelor's in fish and wildlife management from Montana State University and a master's in ecology from Utah State University. He works with private, state, and federal partners to conserve and restore native fishes in the Intermountain West. His presentation this evening, The Ice Age Legacy of Western Fish, How One Rodent Can Turn Back the Clock on Climate Change. Well, thank you very much.
All right, thank you. I appreciate all of you coming out tonight. I did most of my field work for this dissertation based out of Sheridan. We're just over in the dorms. So it feels nice. Sheridan's kind of second home for me in Wyoming here, and feels right to come at the end of the PhD and give a little presentation on the whole dissertation. So today's talk, I'm going to break it up into 4 different parts, and the first couple of parts are going to be kind of background overview about ice ages and about the history of North America before we get into talking about fish and kind of my primary work. I apologize, some of the text is going to be messed up. I took a risk, didn't pay off. The fonts didn't translate, so my bad on the fonts here. So part 1 is Paleo North America. Now I wanted to start where probably a lot of folks are most familiar, which is North America at the end of the Cretaceous. So this is right when the asteroid came and hit and wiped out the dinosaurs. This is what North America looks like. We had this big inland sea that basically separated the 2 halves of North America. And this is why we get such diversity of dinosaurs and inland sea creatures in eastern Wyoming, is because we were right on the edge of that inland sea, right where the conditions were right for them to be buried and turned into fossils, as well as really high diversity. But after the dinosaurs were wiped out, continental drift caused North America to slowly rise over the next 60 million or so years. And so during the tertiary period, this long period that lasted 60 million years, that inland sea slowly drained away. And as it was draining away, we get a lot of the creatures that we know from the Ice Age movies and from museums, stuff like mastodons and mammoths, the large giant sloths, as well as a lot of things that we still have today. So elk, moose, deer, a lot of the critters that we're most familiar with. One thing I didn't know when I started this, which as a guy who's been studying fish for a while now, seems like I would have, is that the river systems for North America were radically different back in this era. And so there used to be what was called the Bell River system, which was an Amazon-sized basin, massive basin that drained much of the North American continent, stretched all the way from Arizona in the Yukon and drained into the Hudson's Bay drainage. And this huge river system was completely disconnected from the Mississippi of today. And so things like the Powder River and the Tongue River all would have flowed north into this Bell River system and had a completely unique fish assemblage as well. But at the end of this tertiary period, because of a number of different factors, probably most importantly, which was as the Earth is orbiting around the sun, it's got a little wobble to it, and the shape of that of the orbit changes slightly over time. We entered an ice age because all the right conditions happened at the right time. And so what happened was this large glacier, this ice sheet, slowly moved down across North America and forced that Bell River system to divert southward. And as it diverted southward, it started emptying into the Mississippi and formed what is now today the Missouri River Basin. So the native fish fauna that was in that Bell River system was completely extirpated. Everything that was unique to that system went extinct. And all the animals that we see now today had to find somewhere to exist during this ice age. They had to ride out the cold and icy conditions somewhere. So this is a graph showing that I'm kind of telling us like you get one big ice sheet that pushed that river south and then it disappeared over time. And that's oversimplifying the story. Over the past 500,000 years, there's been a number of these cycles of ice ages and what we call interglacial periods or warming periods. And so you can just see as about every 100,000 years, we get another advance of that ice sheet. So it would have been flowing back and forth across the continent. And basically during the ice ages, cold adapted species would have been doing better. And during the interglacial periods, the warm adapted species would have been doing better. And so during those glacial periods, species would have existed in what we call refugia, glacial refugia. And the three main ones when it comes to fish are the Pacific refugia, so this kind of ice-free zone down by California, the Southwestern refugia, and the Southern Great Plains refugia. And some of the fish that we're most familiar with today come from each of these three refugia and would have repopulated this area from these areas. So the Pacific refugia had the state cutthroat trout, mottled sculpin, as well as things like red-side shiners. The Southwestern refugia would have had a lot of the species that are native today in southwestern Wyoming, things like the bluehead sucker, Colorado pike minnow, speckled dace. And then the Plains refugia would have had a lot of different minnow and sucker species, things like red belly dace and lake chub, as well as probably the more well-known channel catfish. And what's really cool is that we can actually tell which fish got here right at the end of the ice age and which got here much later. And that's unique to river systems, but to understand why that is, I'm gonna have to talk a little bit about glacial lakes. So the way a glacial lake might form, if we have this cartoon river and the flows going from left to right with this tributary coming in from the north, you might have a system that has a waterfall on it and the trout or whatever fish are unable to advance upstream past that waterfall. Now, what happens when an area becomes glaciated is a lot of times the glaciers follow tributaries. And so as the glacier is coming down, it can block that main stem river and form a glacial lake. And what happens is that in certain circumstances, that glacial lake will back up over the top of that waterfall, making it passable only when this glacial lake forms. And so then your cutthroat trout can get up and over that waterfall and populate the basin upstream of there. Then when it recedes, you have the population on both sides of the waterfall, and anything that only exists below that waterfall, we know showed up after those lakes drained. And this way we can tell which species got here right at the end of the ice age as those glacial lakes were forming and being blown out, and which ones got here later. And this is what we call glacial relic fishes. And perhaps what is most important today is actually a glacial lake that formed up in Montana, Glacial Lake Great Falls. And Glacial Lake Great Falls, if any of you have been up to Great Falls, you've probably seen the big series of cascades on the Missouri River. They're not quite as dramatic as they used to be now because they've got hydro dams and stuff on them. But the fish during the end of the ice age would have been able to get up and over Great Falls, at least early in that glacial period as the glaciers are receding. And so anything that's native upstream in the Missouri River Basin, we know to this whole area was a glacial relic, something that got here early. And so some of those glacial relic fishes for Wyoming and Montana are cutthroat trout and mottled sculpin, speckled dace down in the southwest, as well as red-bellied dace and lake chub, which are little minnows that we find out here on the prairie. So one question that might come up in your mind as you're looking at this series of glacial and interglacial periods is that we are actually in an interglacial right now. And so we have been warming for thousands of years. So as we're thinking about climate change, why is it such a concern that things are getting warmer if we're already in one of these warming interglacial periods? That's going to bring me to part 2 of our talk, which is the Anthropocene. So one thing that we've known about since the mid-1800s is the greenhouse gas effect. And what we see is that global CO2 concentrations in the atmosphere are very tightly coupled to global temperatures. So this is a graph from the past 500,000 years, and doesn't take a statistician to see that there's a pretty strong correlation between atmospheric CO2 and global temperatures. And what you also see is that we're blowing through the historical amount of CO2 in the atmosphere because of our current emissions, CO2 emissions. And so here's a graph of average global temperatures since 1850. So each single line here basically corresponds to the temperature in a single year. And the bluer it is, it means it's colder than pre-industrial averages, and the warmer colors are warmer than pre-industrial averages. And what we see is that in the past 100 years, we've gone up by 1.2 degrees Celsius. Sometimes you'll see 1.3 in the literature, but that's about where we're sitting at right now. Now, that might not sound like a lot as an average global temperature increase, but for context, as the glaciers were receding at the end of the last ice age and things were getting warmer over time, the greatest rate that we warmed at was about 1 degree over 1,000 years. So we've managed to pack that into 100 years. And speed is what kills in ecology. Things need time to adapt to changing conditions. And when you heat something up as quickly as we are right now, species go extinct. And what's unfortunate is we do not seem to be getting it together in terms of reducing our greenhouse gas emissions. So this is from the latest climate change report from the Intergovernmental Panel on Climate Change. And each of these different blocks represents different scenarios for greenhouse gas emissions. And so if we, as a globe, are able to get emissions under control relatively quickly, we can maintain a relatively low amount of warming. But the longer it takes for us to reduce emissions, it's about 4 degrees on the top there. I know you can't see it. Basically, the less we get, reduce our emissions, the warmer it's going to get by the end of the century. And unfortunately, we are right towards the top. So we are going to be pushing 3 degrees Celsius of warming by the end of the century unless we radically reduce emissions. And why this matters is that for every degree that we go up, things get infinitely worse because there are knock-on effects of that warming temperature. We get massive changes in precipitation across the globe, a lot of areas that are going to be experiencing drought, some areas that will be getting flooding, sea level rise across the globe, higher temperatures that then lead to more wildfires, species extinctions, health-related crises as diseases are able to populate areas that they didn't used to be able to tolerate. The point is, there's going to be a lot of negative consequences for every increment of warming that we experience. Okay, so how do fish, glacial relics in particular, relate to global warming? Well, part of my job during my Ph.D. and even a little bit before that has been trying to determine which of all the native fish across Montana and Wyoming are going to be vulnerable to climate change, which is one of these things that sounds like we'd already know it, but we don't. We have an idea of a few species that might decline. Cutthroat trout is one that probably heard about quite a bit, but a lot of species we don't know whether they'll increase or decrease. So that's been my job for the past 5 years. I'm going to show you a little bit about how we go about determining which species are vulnerable. So the first thing we do is we basically scoured all of these different data sources, different agencies, Wyoming Game and Fish, Montana Fish, Wildlife and Parks, the universities, and built this big data set of where fish have been surveyed across the region. And so underlying this, you can see we also have a map of stream temperatures across that region. And what we can do is line these up, and for every single species, we can say, well, what temperatures are they currently at? And that may give us an idea of what they can tolerate. So here I have a Rocky Mountain sculpin, and the little blue dots show where they occur. And what we can do is then determine the upper limit in that range. So about 15.5 degrees C is where Rocky Mountain sculpin populations become pretty small. We don't think they can really exist above that threshold. Then we look at that threshold and say, well, how far past that, at what part of the range is it going to exceed that 15.5 threshold in the area? So we look at the end of century stream temperature projections and just say, how much is it going to be too warm? And for this particular species, it's about 32% of their current distribution is expected to get too warm, to sustain populations in the long term. So this is what my list of vulnerable fishes looked like a couple of years ago. So this is the expected proportion of their loss, and then this is the species on the y-axis. And you can see we have pretty wide variety. Some of the species we expect about half of their range to be too warm, and some of the other ones have virtually none of their range is expected to be too warm. So I'm sitting at a coffee shop in Laramie. I've just developed this, and I'm reading a paper on glacial relic fishes. And I flip to the back and I'm looking at an appendix that talks about, here's the fish that got to our region first, here are the glacial relics, and here's those later colonizing non-glacial relic species. And that list of glacial relics is my list of the most vulnerable fish. This is my one eureka moment I've ever had as a scientist, sitting in a coffee shop in Laramie going, oh, it all makes sense. So the hypothesis is that because these fish were the ones that were getting here first, they were the cold tolerant species that were able to tolerate those edge of the glacier lakes and streams and colonize the area first. And because they're somewhat reliant on colder temperatures, they're also going to be the most vulnerable to warming temperatures. And as evidence, these are the projected losses for glacial relics. On average, we're predicting about a 28% loss in their current distributions. And for the remaining species, the non-glacial relics, only about 9%. But this is all theoretical at this point. This is all just based on models and projections. So, next part of my dissertation was setting out to test this hypothesis, to see are glacial relics actually declining. We've already gone up by 1.2 degrees C. Seems like if this hypothesis is true, we should already be seeing some declines in glacial relics. And so across this large region, this is the Colorado-Wyoming border down here, Canadian border up here. I worked with a bunch of folks to resample sites that had been sampled in the past, to look at what fishes are remaining at over 400 different sites across the region. So what we do is we go back to these sites that have been sampled 20 plus years ago, pull a net through them, count up all the fish, see what species are there. And this is the list of all of the species that we found at fewer sites than they were historically. So got plains minnow, red-bellied dace, flannel mouse suckers, a whole bunch of fish. And then this is the percent of sites where they had become extirpated or were no longer found. So for this northern red-bellied dace, over 50% of the sites where they used to be found, we didn't find them anymore. And when we look at which of these are the glacial relics, we see a good number of them are, about 12 out of the 18. Now, we wouldn't expect every declining fish to be a glacial relic. There's all sorts of things. Some streams are going completely dry. Other fish don't tolerate dams well. So there's other fish that we would expect to be going down, but a good amount of them are the glacial relics. And perhaps the biggest nail in the coffin for these guys is when you look at the overall change in distribution of glacial relics they've already lost, on average, a quarter of their range. Well, if you look at all the other fish combined, they've actually gained in sites. They're found at more sites now than they were 20 years ago. That's on average. But to me, this is pretty strong evidence that glacial relics are more vulnerable to climate change already than they are in the future. Or sorry, than the non-glacial relics are into the future. Okay, so none of this really matters if we don't do anything about it. It's all well and good to know which fish are declining, which ones we expect to do worse with climate change if no action happens on the ground to actually protect those species. And so that's the last part of my talk, how one rodent can turn back the clock. So a lot of you have probably seen in the news that beavers are being promoted for their ability to benefit stream ecosystems. And that big map of all these species that evolved during the last ice age, or before the end of the last ice age, right in the middle there is the beaver. So a lot of these fish, the glacial relics, evolved with beavers. Now, some of the benefits of having beavers on the landscape, this has been studied now for over 50 years, and some of those benefits are pretty obvious and some of them are less obvious. So some things that you see are that wetland plants substantially increase in abundance with beaver ponds. You can see how much greener this area, how much greener, wide the green area is around this beaver pond compared to the stream without beavers on it. The amount of habitat diversity goes up. So there's deep areas and shallow areas, little side channels, whereas in the stream without beavers, pretty much just a single thread channel. And diversity is really good for promoting different types of animals. So you get higher diversity of animals with habitat diversity. You also get greater thermal diversity, not only in the ponds themselves, where you get some level of warming at the top level, you get cooler temperatures down at the bottom, but beaver ponds actually basically can push water into the groundwater and force it downstream. And because it is forced through the ground, it actually cools down. So downstream of beaver ponds can also be substantially cooler than the stream upstream. It raises the water table, which benefits a lot of aquatic species. And then all of the riparian vegetation that grows around these ponds really promotes wildlife diversity as well. We had a project just south of here in Buffalo where we basically mimicked beaver by building fake beaver dams, a whole bunch of them. And over the course of just a couple of years, we saw a 50 times increase in the amount of northern leopard frogs. Basically, they went from not being there at all to seeing them flipping everywhere. So a lot of species benefit from beaver activity. Perhaps one of the most interesting examples of the benefits of beaver is that they can protect streams from wildfire. So this is a landscape that has been completely burned, and you see the only green left in the entire landscape is where you have this complex of beaver dams along the stream bed. Now, despite all of these benefits that we have documented, we know about from beavers, what we don't know as much about is whether or not they're good for fish. There's some evidence for individual species doing pretty well. Cutthroat trout seem to benefit from beaver ponds. A handful of other species that we know do well. But what we really don't know is if prairie fish benefit. And those prairie fish include a lot of those glacial relics, the northern red-bellied dace, the lake chub, things that prefer cooler temperatures. And so what I sought out to do was to find out if fish are benefiting from beaver ponds across the prairie. And so what we did was we sampled beaver ponds from kind of that same area from the Colorado, the Canadian border, across eastern Montana and Wyoming. And we'd pull a net through a beaver pond, count up all the fish that we caught, see what species there were. Then we'd go and we'd find a reach on that same stream that didn't have beavers to compare it as a control, and then see what the differences were. And I just wanted to show kind of what the diversity of beaver ponds can look like out on the landscape. In mountain systems, you see a lot of dams are built of willows and they look pretty similar. On the prairies, that doesn't hold up. There are all sorts of different materials that are built. I know it's a little hard to see, but this one is built entirely of cattails and mud. There's not a willow in sight. Some of them are over my technician Molly, basically as tall as she is. There's this huge diversity of what beaver ponds look like out on the prairie. I saw a picture of one the other day that was entirely built of corn stalks in Iowa. So they're a very resourceful critter, and they build in places where we didn't necessarily think that they would build. And when it comes to the fish species that we see in beaver ponds versus the sites without beaver ponds, we had 3 times higher abundance in the beaver ponds. And that not only holds up for the entire fish community, but for native fish in particular. So it's good for fish in general, and it's especially good for native species. At least that is what the data is showing so far. There is a caveat though, which is that if you have a stream that's dominated already by invasive species like green sunfish or smallmouth bass, brown trout are invasive. If that's what's already in the system and beavers move in and build a beaver pond, that's what you're going to have in your beaver pond. So you're not going to radically change the system. You're just going to basically dial up the abundance of what's already there. And what does this mean for management? Well, there's been a lot of work and activity in the past 5 years in particular to promote beavers on the landscape. So this is a picture of a game and fish biologist over in Cody who is taking beavers that are causing problems, damming up irrigation infrastructure, and they live trap them out and move them into areas where they can be beneficial. And they actually just built a beaver bunkhouse in Cody where they can go out and capture an entire family group of beavers and then house them at this bunkhouse until they can find a place to go and move them. And so one of the areas where this is happening the most is up in the Black Hills. So a lot of the problem beavers are being translocated up into the Black Hills, and the Black Hills are one of the areas that we have the most glacial relics left in the area. So we're already in part doing what is really beneficial for these glacial relics by promoting their abundance with beavers. So to kind of sum up here, in order to promote the abundance of these glacial relics that we know are in decline because of climate change, what we can do is take what is currently a problem, these beavers that are messing up infrastructure, and move them to areas where we have these fish that are vulnerable and basically kill 2 birds with 1 stone. With that, I'd like to thank the National Science Foundation, Forest Service, and USGS for the funding, our cooperators at Game and Fish, Montana Fish, Wildlife and Parks, and the BLM, and take any questions.
Okay, you're moving beavers around where they're problem beavers, but I didn't hear you mention anything about the habitat that beavers are in that they are destroying. You know, they tend to eat themselves out of house and home. So the beavers that you're moving, are they going to end up creating problems for themselves by eating themselves out of house and home?
They tend to, that can happen. You can have a beaver move into an area, and if there isn't enough woody vegetation or cattails or something that they can feed on, they can die out. A lot of times they'll try to migrate before they do that. And as far as causing problems with vegetation that we want to be places, but there's a landowner south of town that I was working with that really didn't want her willows. She liked beavers, but she didn't want her willows to disappear. Some of the big peach willow trees. And you can basically fence those off as well. So I don't know if that answers your question, but they can eat themselves out of house and home. But most places that we move them, they either move themselves if they don't like what's there, or they're able to find it already there.
So has your work with moving beavers been primarily out of the mountains and into the plains type areas?
I don't move beavers. That Game and Fish moves beavers.
Substitute even fish for you.
Well, a lot of times they will move from kind of highly populated areas into more remote areas. So it's probably, I haven't seen any strong data yet. There's still a lot of data being collected about these beavers that are getting moved around the landscape. But I think it's probably more from more urban areas to rural areas.
I'm surprised that the beaver dams result in more cooling of the water. That's interesting.
Yeah, you do tend, the ponds themselves actually do get slightly warmer. If they're really deep, you will get cooler temperatures towards the bottom of those beaver ponds. But because they're forcing that water into the gravel, into the groundwater, that water gets cooler. So it's not strong either way. You don't get massive warming and you don't get massive cooling, but downstream you do get slight. All right. Thanks everyone for, oh yeah, please.
So how the relic fish how do you know that they were there way back 100,000 years ago?
They have to be above those waterfalls that we
Have to
know.
be there still alive.
They have to be there, and they can't be ones that we know were introduced by people.
Okay. So it's not anything fossilized.
No, that tends to, over those lengths of period, you do get evolution of fish, which kind of, you get less strong breakdowns in which ones are colder water species, which are warm water species. So you can't go back too far to determine what a glacial relic is. It's kind of species that we still have on the landscape. So it's really towards the end of the ice age that we're most interested in for determining glacial relics.
Okay.
So, and you said that Bell River system, that's completely gone, all of those.
Yeah,
Are there fossil remains of those fish?
it was under a mile of ice. If there's any, it would be little pockets, but I'm not a geologist, but I'm not aware of any. They were able to tease a lot of that out by actually looking at the delta where it emptied into the Atlantic
Mm.
and I guess the Arctic Ocean, and seeing basically the remnants of chemically what was that
Yeah.
deposited material, and then they could see where it was from. And that's why we know it was in Arizona at one point. There's some of those Arizona basically rocks that were deposited that far downstream.
Wow.
Goodness.
So the Red River that runs between Fargo and Moorhead runs north into Hudson Bay. Is that like a vestige of that Bell River system, or is that just a modern anomaly? Or
It would have formed after that Bell River system. So that whole system got shifted around, and that would have formed once the glaciers were receding. That area in particular was part of it's called Lake Agassiz, big glacial lake that formed in that area, like Lake Manitoba, Lake of the Woods. Some of those areas are remnants of that lake, but all of that is receding glaciers causing that basin to be formed.
So these historical CO2 trends that we see every 100,000 years, and we're getting close to 100,000 years again, is there some way that could help offset some of the man-made CO2?
I've seen a study that came out a couple of years ago that estimated that because of our current emissions, we've actually set back the next ice age by another 50,000 years. So despite the fact that that's taking into account all of that planetary movement,
Wow.
yeah, it's not going to totally offset. the current warming.
I know this doesn't have anything to do with the relevant fish, but like the invasive species like the snakeheads and the Asian carp and those type of fish seem to be really resilient and everything. Is there a chance that they'll like be the only species that'll survive the warmer temperatures or?
No, there are plenty of native fish that are gonna be just fine. A lot of them are warm adapted species as well. But we do risk losing more of the colder water, many of which are those glacial relics fish. One interesting thing that you get with invasive species is that you don't have the natural predators that they had in their native range. So you introduce them somewhere else and they actually do better. Like common carp are at risk in Asia. Over here, they're moving everywhere, going gangbusters. And part of that, at least why we think, is they don't encounter those predators, the diseases. They're basically released from that type of competition. So they will, a lot of them will do very well, but we'll still have other fish.
What about fish like sturgeon and the paddleheads or, those kind of paddlefish? Are they affected much by the warming or the cooling, they're not relic fish, are they?
No, it's not directly. A lot of those big river fish, though, are more strongly affected by dams. A lot of them, sturgeon in particular, they will move upstream to spawn, and their larvae have an obligate drift phase, so they develop as they're drifting downstream. And if you have reservoirs every several hundred miles, they hit that reservoir and sink to the bottom. And so they're affected by human activity, just not climate change in particular, even though there's definitely a possibility that altered flows will impact them, just not warming. Right, well, thanks everyone for coming.
Thank you.
Thank you.